Okay, so for these types of problems where it says calculate and report with the corresponding significant digits, we're going to save the significant digit part for later. So what we're going to do is we're going to take what they give us, right? So right now it's 120 grams of water. And we're going to figure out how to calculate what it wants us. So it wants moles. I know that molar mass deals with grams and moles. Okay, so I know that what we just did, the molar mass, we can use for here. So it's going to be some amount of grams equals 1 mole. Now, to figure out how many grams are in 1 mole of this substance, water, we have to find out the molar mass. We know oxygen equals 15.999. We know hydrogen is 1.008. We know there's 2 hydrogens. Okay. There we go. So that equals 2.016 and 15.999, which means when we add them, we end up with 5,1,0,1. Okay, here we go. So we got 15, 16, 17, 18, 18.015 grams per mole. All right, so we can plug that in. 18.015 grams for every 1 mole of water. Okay, so now we're going to plug this into our calculators. So we got 120, and we're going to hit the divide button, because the 18 is below on our dimensional analysis schema. So we got 18.015. Okay, we see 120 divided by 18.015. We make 6.66. All right. Get rid of that real fast. Whee. All right. 6.66, and it's moles of water. But now we'll go to the sig figs. So if you look here, there's no decimal, so there's only the non-zeros count here. So the 1 and the 2, so that's 2 digits. So our answer should be written in 2 digits because we were doing multiplication and division. Alrighty, so 6 point, the other 6 makes the middle 6 go up, so 6.7 moles of water. Whee. Okay. All right, let's try this next one. This next one is talking about how many grams are in 4.00 moles. So they told us how much? 4.00 mole, okay, of NH3, ammonia. Okay. We're going to do the same thing that we did before, but different. So see how we have moles now instead of grams? Okay. So we're going to have moles down here. And it says how many grams. So we want some amount of grams. So knowing this, right, we just saw the same thing, but it's reversed. So instead of moles on top and grams on the bottom, it's reversed. So it's grams and then moles. But look out, if you just plugged in that 18.015, that's for water. We want ammonia. Now, if you're like me, you noticed that you already did ammonia. Ammonia's molar mass is 17.031. Okay, so 17.031 grams for 1 mole. And that's going to make some amount of grams. So we're going to plug it in to our calculator. 4 times, right? 4 times 17.031. And we get 68.124. Now we can't leave it like this, right? Because we're still using the right number of sig figs. And it says we have 1, 2, 3. There's a decimal. So these zeros after the decimal count. So 1, 2, 3. Our answer should be in 3 digits. So it's going to be 68, and the third digit is this 1. The 2 doesn't make it round up, so it's still 1. Grams of ammonia. Okay? So that would be our answer. Okay. Now this one's going to be a little bit of fun. Because now they're saying we're starting with atoms. So we're going to still write it the same. So we're going to write 9.23 times 10 to the 22nd. It says 22nd. Careful with that. Alrighty. Now, it's atoms. That's a lot of atoms. Let's think. It wants how many grams? So we want to end with grams. We got atoms. So a good middle person, I know, is the mole. So we got to get from atoms to moles, and then moles we can get to grams, right? We can use a molar mass to get from mole to grams. All right, so let's do this. So we got atoms. How much is 1 mole of anything? Well, we got to look. Okay, 1 mole equals that many pieces. 6.02 times 10 to the 23rd of anything. It could be molecules, it could be atoms, but it's always going to be 6.02 times 10 to the 23rd, and that's going to make 1 mole. All right, so now, right, these will work, and then we have mole, so 1 mole of aluminum is so many grams. So we can look on the periodic table. We go, ooh, aluminum, 26.982. 26.982. And now we can plug it into our calculators. Okay, 9.23. And the way you can do this times 10, I do on this type of calculator, okay? Second button, and you see this EE? That's what I'm going to use. And 22, okay? Sometimes if you don't put the parentheses, it's going to think that you're still doing the times 10 to the whatever. So I put in parentheses. So this number is entered, and we're going to divide it by the 6.02. This time I remembered to use my parentheses. 6.02. See, second button, E, 23 times 26.982. Okay, and there's our answer. See how I didn't have to do any of this middle steps? I just typed it all in, and now I get 4.13694, blah, 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 grams. Okay, and again, sig figs. We've got 1, 2, 3. So our answer should have 1, 2, 3. This guy, 4.14 grams of aluminum. Alrighty, so that's how we figure out the mass. So D, it's operating a little bit differently. So this one, they tell you you have 30 liters. 30 liters of oxygen. They want to know how many molecules. So they're telling us that we're going to assume 24 liters for 1 mole gas at room temperature, which is about 25 degrees Celsius. So 24 liters equals 1 mole. Okay, but how many molecules is 1 mole? So 1 mole, right? So liters cancel with liters, mole cancel with mole, and get left with particles, pieces. Okay, so again, 6.02 times 10 to the 23rd. Because we're trying to get to molecules. If it said atoms, you could also do that, right? So 6.02 times 10 to the 23rd. Okay, so we're gonna type it in. 30 divide by 24 times 6.02 times 10 to the 23rd. Okay, and we end up with 7.525 to the 23rd. Okay. 7.525 times 10 to the 23rd. Okay, we have to double check. Make sure we have the right number of digits. Oh, so the number we were given was 30. The only significant digit is the 3. So we're going to round to the first digit, which makes it 8 times 10 to the 23rd. Molecules. Alrighty. We can do now this same thing, but instead of 24 liters at room temperature, let's assume that it's going to be 22.4 liters at 0 degrees Celsius. So if this gas was still 30 liters at 0 degrees Celsius, it would have a different amount of molecules. Okay, because as temperature goes down, the volume should go down. But if it didn't, if it's 30 liters, so I'm going to make sure I record this. So room temperature, RTP, which means room temperature and pressure. This one's going to be STP, standard temperature and pressure. Okay, so 30 liters, and we're just going to do this exact same thing, but instead of 24, it's going to be 22.4. Most of the time, they'll tell you in the question whether it's STP or RTP. All right, 1 mole. And sometimes they'll even give you the amount in the question. And we know 1 mole equals 6.02 times 10 to the 23rd. And we get 30 divide 22.4 times 6.02 times 10 to the 23rd. We get 8.0625 times 10 to the 23rd, which is really 8 times 10 to the 23rd molecules. Oxygen. Right? How interesting, they end up being the same, but different. So even though they were different amounts, because it wasn't very, there weren't many significant figures, significant digits, it ended up being the same-ish value, even though this one was 7.5 and this one's 8.0. It still ended up being 8 times 10 to the 23rd molecules of oxygen because of the significant digits. Questions with percent error may come up, and you have to look at the percent error equation, the formula for percent error. So it says percent error, so that's what it is. Percent error equals experimental minus accepted divided by accepted times 100. Okay? So let's go ahead and do this. So they tell us if a student were trying to find density of aluminum, they found 4.3 grams per centimeter cubed, which is just amount of density. So they found 4.3. The actual, so the accepted value is 2.7. So we're just going to plug these numbers in. 4.3 minus 2.7 divided by 2.7 times 100. Okay, so be careful in your calculators. This top piece has to be done first. Alrighty, so what we're going to do is we're going to use these parentheses again. 4.3 minus 2.7, back parenthesis, there we go. And then we can do our whole division and multiplication thing together. 2.7 times 100, all right. And we get 59.259. All right, let's look at significant digits. This one, and we're going to 59%, because we've got the second digit. This problem is a lot more complicated because it's not just giving you the percent error issue. So remember, percent error is right on the back of your periodic table. It tells you percent error, experimental value minus accepted divided by accepted. So experimental minus accepted divided by accepted times 100. Alrighty. So here, what we're going to do is we're going to read this through, make sure we understand the whole thing. So they're calculating how many moles of methane are in this many grams. So John already calculated. He found his answer to be 6 moles. Okay? So this is what his experimental value is. So if we want to put this to the side, 6 minus something divided by something times 100 is going to be our percent error. Okay? We don't know what that something is because we have to calculate it. So first, we have to figure out, okay? So they said they had exactly 90.56 grams. Okay? So getting grams to moles, because that's what they're trying to figure out. 1 mole, we know we can use the molar mass to figure that out. So finding the molar mass, right? We find carbon, it's 12.011. 12.011. And we know hydrogen is 1.008. Same way we found the carbon. Now, if we look at the formula, carbon is only 1 of them, but hydrogen is 4 of them. All right, 1.008 times 4 plus 12.011. Okay, it's 16.043. Grams per mole. So, for every 1 mole is going to be 16.043 grams. All right. So 90.56 divided by 16.043 make 5.6448. Okay. So since we're still not done with what we're trying to figure out, we're going to keep these digits. Theoretically, you could just keep the 4. 1, 2, 3, 4. That's fine. But I'm going to keep all these. So 5.6448, 5.6448, because we know that this has to be the exact number, because all we did was look at the exact number on the periodic table, and we divide using their 4-digit number. Okay, So that number divided by 16 gave us this. And so this is what it should have been. And so when we type it in, we get 6 take away what we found. Okay. Right? Divided by what we found times 100. And that makes a total of 6.29%. Now, because all we had to work with was that 6, our value here, so he was 6% wrong. Alrighty.